Welcome to this fifth lecture on this NPTEL course on fluid mechanics for undergraduate students in chemical engineering. In the last lecture, we discussed the basic difference between Newtonian fluids, viscous fluids and elastic solids, and we wrote down, we said that suppose you take two plates and place a fluid layer in between them, okay, a layer of fluid in between them. So, let me just remove. So, this is the layer, this is fluid in between, and suppose you exert a force on the top plate F x. Okay. So, the top plate itself, if you recall, is a plate that is extending in the z direction, where the coordinates are as follows: x, y and z. Okay. So, this has an width w in the z direction, okay, and this is the area, the top area A, over which the force F is being applied. Okay. And if the bottom plate is stationary, no force is being applied and it is stationary, okay, then we said that if you follow line, if you follow a colored line in the fluid which was vertical before the application of force, and if you follow the line after the application of force, this line will continue to tilt as a function of time. So, here time increases, increasing time, okay, in this way. T, as time t increases, this line will keep on tilting. So, a fluid continues to deform upon application of tangential or shear stress, shear force, in contrast to a solid which deforms to some extent and then stops deforming upon application of force. So, we said that the stress is force divided by unit area, force divided by the area upon which the force is acting. The stress is actually denoted by the symbol tau, and we said that there are two suffixes for the stress. X is the direction of the force, and y is the direction perpendicular to the surface upon which the force is acting. So, it is the direction of the unit normal to the surface, unit vector perpendicular to the surface is called unit normal. Okay. So, it is the direction of the unit normal to the surface upon which the force is acting. So, this is the stress, this is the definition of a stress. So, tau y x, we said, must be proportional to the rate of deformation, which, if you recall, we call this angle as delta alpha. Okay. Since delta alpha continues to change with time, we said that the stress must be proportional to delta alpha by delta t, and this was also found to be equal to, based on geometric considerations. If you recall, this was the line before deformation, this is, let us say, delta alpha, and this is the small displacement delta L, and this is the thickness of the fluid H, and delta alpha, tan of delta alpha is delta L by H, but for small enough angles this is approximately equal to delta alpha is delta L by H. But as the fluid deforms continuously, the top plate will move with a velocity v, let us say, or let us say u. Okay. So, delta L is u delta t. Okay. So, delta alpha is u delta t divided by h, or delta alpha by delta t is u divided by h. Okay. So, tau y x must be proportional to u, which is the velocity at which the plate is moving, and divided by the gap thickness in which the fluid is moving, and the constant of proportionality is the viscosity of the fluid. Okay. This is the viscosity of the fluid. and we also gave you some examples of viscosity values. Viscosity of the fluid is measured in Pascal second in SI units. Okay. And we also gave you some examples of the values of viscosities of various commonly encountered fluids like air, water, oils and so on. Okay. Now, what is the use of this formula? Well, we will return to this formula in detail later when we do differential balances, but at the outset this is an introduction to how a viscous fluid behaves upon application of shear stress. You can use this formula to find, for example, suppose you have a fluid layer, okay, a viscous liquid, and let us say you have to push this viscous liquid, and the bottom you have the bottom surface is stationary, and let us say you are moving the top surface with a belt with a velocity. Okay. So, this is rotating. So, this is a velocity u at which the belt is moving. So, you are trying to drag the fluid at a constant velocity. Suppose you ask the question, what is the force that must be exerted to move the fluid at a velocity u. Suppose you ask this question, well, the answer is obtained in the following way. We know that tau yx is the force F x divided by A, the area of the belt. So, remember these are all, the belt is a finite. So, this whole sheet is, so this is a roll, cylindrical roll in the third direction, and this whole roll is rotating, okay, at a constant velocity, and the area of the top plate is, or the belt surface is A. So, that is the area. So, this is the viscosity of the fluid times u divided by the gap thickness. So, force is therefore mu A u divided by h. Suppose we know the values. Suppose you are interested in dragging a viscous liquid using a belt. Let us say example, viscosity is, let us say 0.01 Pascal second. Let us say the gap thickness is 1 centimeter, okay, and the area is, so we should convert this in SI units, which is 10 to the minus 2 meters. Let us say the area is 10 centimeters by 10 centimeters. So, this is 10 to the minus 2 meters times 10 to the minus 2 meters, which is 10 to the minus 4 meters squared, and let us say the velocity is 1 centimeter per second, which is 10 to the minus 2 meter per second. Okay. So, if you substitute everything in that expression, f x is mu, which is 10 to the minus 2, 0.01 Pascal second is 10 to the minus 2 times, so let me just write this as 10 to the minus 2 Pascal second. So, 10 to the minus 2 times area is 10 to the minus 4 times velocity is 10 to the minus 2 divided by h is 10 to the minus 2. Okay. So, this is about 10 to the minus 6, okay, newtons. Okay. If the area is just this small amount, then this is the force that must be exerted to move the belt at a constant velocity. What is the rate at which work must be done? Suppose you want to move this conveyor belt using some rotating machinery. So, the rate at which work must be done by the machinery in order to keep moving this is, work must be done by the external agency. To move this belt is, work done is force times distance, rate at which work done is force times distance divided by time. Distance by time is velocity. So, it is the force times velocity, okay, it is 10 to the minus 6, okay, times velocity is 10 to the minus 2. Okay. So, this is 10 to the minus 8. So, this is Newton, then meter per second. Okay. So, this is the rate at which work is done in order to move this fluid. So, this is one simple example of this equation that we just wrote down for a simple fluid. So, we also said that this this relation mu u by h, okay, this describes what are called Newtonian fluids. Okay. Because this is only an expectation that the stress must be directly proportional to the rate of deformation, but it turns out that many commonly encountered liquids respect this expectation. So, this is a material behavior, okay, and we will see that such relations are called constitutive relations later. These describe specific behavior of how a given fluid flows or responds to external applied stresses. Okay. And there are fluids which do not obey this, for example, slurries and solutions of polymers, molten plastics and so on. Such fluids are called non-Newtonian fluids. Anything that does not obey, okay, if this is not obeyed, they are called non-Newtonian fluids. So, things that obey this, they are called Newtonian fluids. Okay. So, we will discuss much later in this series of lectures as to how to understand the behavior of non-Newtonian fluids a little later. Okay. So, this expression for the shear stress as a function of velocity of the top plate divided by thickness was applied to a case of a finite fluid layer of thickness h, which is exerted upon which a force is exerted in the x direction and so on. But you can also think of a flow. Suppose you have the same example, a flow is here is the xy coordinate, okay, this is fluid in between. You can also think of considering a tiny slice of thickness delta y in the y direction. So, essentially if you recall, we are extending everything in the z direction. So, this is a tiny slice like this of thickness delta y in the y direction, okay. And you can try to apply. So, when the fluid is stationary here, the fluid is moving with some velocity here, okay. So, if you were to plot the velocity, so the velocity will go from 0 to some velocity u at the top plate in this example, okay. So, fluid layers are sliding past each other in this simple example. So, if you take a tiny slice, okay, like so, the fluid that is flowing past here will have a greater velocity than the fluid that is flowing below this tiny slice. So, if you are moving with the velocity of this lower fluid, the flow about this tiny slice will again appear. So, I am just expanding this tiny slice, will appear like a linear flow like this, okay. Okay, so, the thickness is delta y. So, because these two slices are fluid above the slice is moving with a greater velocity than the fluid below the slice. So, if you move with the velocity of the lower side, then this will appear stationary, the top will appear to move at a constant velocity. So, this expression can be generalized, okay, in the limit, okay, delta t going to 0, delta alpha by delta t. This was the fundamental definition, and delta alpha is by delta t is nothing but limit delta t tending to 0, delta u by delta y, where delta u is the difference in velocity between these 2 points. Okay. So, we know that if you take a slice, okay, this magnitude of the velocity differs between these 2 slices in this case. So, that magnitude of the velocity difference is delta u. So, as delta t goes to 0, this is the shear stress, this is mu times this. So, tau y x is mu du dy in the limit of delta t goes to 0, okay. The velocity difference, so this translates to delta y goes to 0, okay, becomes this. Okay. So, this equation is not merely applicable for thicknesses of macroscopic dimensions. Even if you take a tiny slice, volume slice, and then we try to look at how flow is going to happen, how the shear stresses are related, okay, we will find that this is true even for a tiny slice. Okay. So, this is called the Newton's law of viscosity. Okay. Now, the next topic that we are going to discuss is fluid statics, but before I do that, we will have to first understand what are the various forces that are exerted on a given fluid element. Okay. So, let us continue along the same lines and then try to classify the types of forces that can be experienced by a given fluid element, volume element of a fluid, and then we will proceed to fluid statics. Okay. So, let us imagine having continuing with the same example. Okay, you have two plates. Okay. So, the thickness is h, this is x, this is y, this is z, okay, and the top plate is moving with a velocity let us say capital V, the bottom plate is stationary. Okay. So, if you consider a tiny volume element, okay, remember that z is going outside into the board. So, essentially this volume element will look like this, okay, into the z direction, into the so the z direction is going into the board. Okay. So, but this is the volume element, okay, this is the volume element, but if I want to write it in so let me draw it separately, here. So, the volume element that we are going to analyze is something like this, but in a 2D plane, because this diagram has been drawn in a plane that is cutting across any z location, the volume element will appear like a slice. Okay. So, this volume element, what are the forces that are acted upon on this volume element? Suppose you are doing this experiment in a lab and let us say gravity is acting downwards. Okay. Now, if you take this, let us for simplicity assume this to be a cubic volume, that simplifies our discussion. So, take a cubic volume element instead of a rectangular volume element. So, this will appear like a square in the 2D diagram. Okay. What are the forces on this volume element? Well, if the volume of this cubic volume element is delta V, because there is gravity, okay, there will be a force. See, whenever gravity acts on a mass, there is a force acting in the direction of gravity mg. So, mass times acceleration due to gravity is a force. Okay. This force acts through the entire body, entire volume. Okay. Such forces which act through the entire volume are called body forces, or sometimes they are also called as volume forces, because if you take a tiny volume, this force due to acceleration due to gravity acts through the entire volume, not just on a particular surface or a given location. Okay. So, it acts on the entire volume. So, this body force acting on this volume element, okay, and the body force is acting in the y direction only, because we know that gravity is only in the we have aligned the gravity in the direction of negative y. So, this is negative because gravity is acting. So, this is the direction of positive y, gravity is pointing in the direction of negative y. So, that must be negative. Mass is density of the fluid times the volume, infinitesimal volume we are considering, times acceleration due to gravity, the magnitude of acceleration to gravity, which is 9.8 meter per second squared in SI units. Okay. So, this is the force that is acting on this volume element due to acceleration due to gravity. Okay. Such forces are called body forces or volume forces. Okay. Now, apart from this, because of the fact that the top plate is moving with a constant velocity, so I told you that, okay, so something like this should happen. So, there will be fluid flow layer by layer in this simple case. Okay. And if you take a tiny volume element, I am exaggerating this volume element for illustration's sake, but this is a very tiny volume element. If you take a tiny volume element, okay, let us again draw this square separately here. Okay. So, there is fluid flow above the square with some velocity and below the square with some velocity. Okay. And this difference in velocity means that there is a shear stress exerted by the fluid on the top on this surface. Okay. Such forces which act, suppose you consider this, remember that it is a cubic volume, it has a surface on the top, I am drawing the 2D version of it. So, there is a surface. So, along this surface, the top surface, okay, there is a force that is acting in the x direction due to the fact that fluid layers are flowing past this surface, and due to viscous action there is a stress or force per unit area or a stress. Such forces are called surface forces. They act only on the surface, okay, of a volume element. Of a fluid element. When I say fluid element, we mean a volume element in the fluid. Okay. So, if you take this volume element, there is a tangential force on the top surface due to the fluid flow above, okay, in this direction, and this will constitute a surface force. This is essentially due to the tangential forces due to viscous action, but there could also be force due to in the normal direction due to pressure. Those are also surface forces. Okay. So, surface forces can be acting normal to a surface and tangential to the surface. The normal force to the surface is usually pressure, dictated by pressure. Also, we will clarify a little later when we do differential balances this statement, but you can think of at this introductory level normal force on an element on a surface largely due to pressure. This is acting perpendicular to the surface. So, it is normal, therefore, it is a normal force, whereas the tangential force is acting parallel to the surface, that is why it is called tangential or shear force. So, pressure forces and shear forces can act on a surface, and these are all acting only on a surface and not to the entire volume. So, these are called surface forces. Okay. So, this is in the context of a simple example like this, like flow between two plates, but in general you could have a fluid, okay, that is flowing in an arbitrary way, and you can construct any volume element. So, okay, any arbitrary volume element, okay, and this volume element will have a surface, and the surface is characterized. So, this is the volume element. So, this is a volume element in 3D, it is arbitrarily shaped, but since I can draw only a 2D version in this board. So, I have drawn a 2D version and the unit normal to the surface is n. Okay. So, the n, suppose you consider this, let me draw this slightly better. Okay. So, this is the arbitrary surface. At each and every point this n will keep varying. So, n will be like this here, like this here, like this here, and like this here, and so on. So, n keeps changing. This is an arbitrary volume element in the fluid, in a fluid flow. Okay. So, this arbitrary volume element in a fluid flow is surrounded by fluid also. Okay. So, this is surrounded by fluid. Okay. And if you look at a given point on this volume element, okay, and you worry about let us say you take a tiny patch of area delta A, okay, this as a unit normal n at this location. And if you ask what is the force can in general be in any direction, or the force per unit area, which is denoted by the letter R, it is the stress vector, okay, it can point in any direction. So, let me just illustrate this again separately. So, you take any surface on a volume element, take a point P on a volume element, on the surface of a volume element, and the surface has a unit outward normal n, okay, and the force that is exerted by the fluid that surrounding on this, the surface force that is exerted by the fluid that surrounding this area on this surface can in general point in any direction. Okay. So, that force is denoted by R. Okay. This is the area. Okay. Now, this R is of the force, and that need not in general be in the direction of the normal, okay, but it will have a component perpendicular in the direction of the normal. So, let us call that. So, I am going to draw this again here. So, this is R. The component of R in the direction of the normal is called the normal force per unit area. So, R is the surface force per unit area. Okay. So, there is a normal component Rn, and along the surface there are two tangential components RT1 and RT2. Okay. So, this is the normal stress, these are the tangential stresses. Okay. To any surface you can construct a normal, unit outward normal, and you can for this normal, okay, perpendicular to this normal, there are two tangential vectors. This can be constructed in any way that you want. I am just showing it for illustration in this manner. Okay. So, this force that is exerted by the fluid on the outside on this surface can be resolved in the direction of the normal as well as in the direction perpendicular to the normal, that is parallel to the surface itself. So, the surface force can have in general a normal component. This is the surface force, remember, can have a normal component as well as tangential component. Okay. Now, and I have given you a simple example that the surface forces normal as well as tangential components. मोबाइल को स्विच ऑफ कर लेते हैं. So, the surface forces can have normal as well as tangential components. Okay. Now, I have given you some simple illustration in which the tangential component of the surface force, why it occurs due to viscous action, but we will discuss more about this in detail a little later. Clear understanding of what are the forces that can be exerted on a volume element of fluid is necessary to understand how to analyze fluid mechanics. Okay. Because ultimately, as I told you, fluid mechanics is a branch of mechanics, and if you take any tiny volume element, okay, and if you know what are the forces that are acting, the body force, which is rho g delta v, and the surface forces, if you have a knowledge of body and surface forces, then one can apply Newton's second law of motion, that is, which says as mass times acceleration is sum of all forces, okay, which can be used to compute the motion of the fluid. So, this is the program, rough program in any branch of mechanics, but in fluid mechanics the forces are not of various types. One is the body force, which is acting entirely through the volume, and the other is the surface force, which acts only on the surface. The surface forces can be due to viscous action and as well as due to pressure. Okay. So, the first topic that we are going to consider is fluid statics. Okay. Now, we are going to consider fluid statics deals with a fluid that has no motion, that is no flow. Okay. So, there is no flow, there is only the fluid is stationary. Still there are some interesting aspects to the force distributions even in a fluid that is even in a fluid that is not moving, so it is just stationary. Okay. So, let us understand what forces can act on a static fluid. You take a fluid volume, construct a surface, okay. At any point you take a point in the volume, construct a surface, okay, of area delta A. This surface is denoted by unit normal n. So, in general the surface forces are in the direction of n, which is what I call R n, okay, and in the direction perpendicular to n, which is what I call R T 1, the tangential forces. These are the shear forces. Okay. Now, we are now considering fluids that are not moving. A fluid is static, the fluid is static. Okay. Now, what can we say about the forces, the nature of surface forces when the fluid is static? By definition, a fluid undergoes a flow when there is a non-zero shear stress. We just saw this in detail in the last lecture, where we constructed simple thought experiments where it showed that a fluid continues to deform upon application of shear or tangential stresses. So, if you consider a fluid that has no motion, no velocity and no flow, then it implies that the fluid, the tangential stresses in the static fluid must be 0. So, the tangential stresses must be 0 in a static fluid. Okay. So, you cannot have tangential stresses. So, the only type of surface forces that can act on a volume element, so the only surface force is the normal force, because if there is a tangential force on any point in a fluid, that means that the fluid will start flowing, because a fluid cannot resist any non-zero tangential stress. Even at a slightest application of tangential stress, the fluid will start moving. Okay. So, therefore, we can conclude safely that in a static fluid the tangential stresses are 0. Okay. So, 0 tangential stresses. And the only surface forces must be purely normal to any surface. Okay. All right. So, now this is true for, suppose you take a static fluid and consider a volume. Okay. Let us take a simple volume like a cube. Okay. So, if you take any phase on this volume, if you take the top phase, the forces will be purely normal if the fluid is static, because there is no way the fluid can support a tangential stress. If you take the side phase, here again the forces will be purely normal, and same with bottom and so on. So, the forces will be purely normal in a static fluid, but this is true for any volume element, because you can construct a volume element, the shape of the volume can be as arbitrary as you please. Even in this complicated volume element, the forces will be purely acting at each and every point on the surface of this volume element. The forces has to be purely normal, because by definition in a static fluid, okay, in a static fluid, if you construct a volume, okay, arbitrary volume element, okay, the forces have to be purely normal, because at each and every point in the fluid, if there cannot be any tangential stress. Okay. So, the normal force in a static fluid, so there can in general be normal forces. A static fluid can support normal forces. The normal force exerted per unit area is usually compressive in nature in a fluid. That is, if you consider this is the fluid inside the volume element, this is the fluid outside. Okay. So, this fluid outside exerts a force that is compressive, it tends to compress the fluid inside the volume element, but the unit outward normal is pointing like this, okay, to this volume element. At each and every point on the surface, the unit outward normal will act like this, but the normal force will act in the direction, this is the direction of the force, in the direction opposite to the unit outward normal. Okay. This normal force exerted per unit area, this compressive normal force exerted per unit area in a fluid is called the pressure. Since it is force per unit area, it has dimensions of newtons per meter square. The normal force that is experienced by a fluid, a static fluid element, volume element, okay, the fluid is static. So, if you take a volume element, I have just told you that this volume element in a static fluid will experience only a surface force that is purely normal to each and every point on the surface, and this is compressive in nature, that is called the pressure. Okay. So, if you say this is n, okay, and if you say r vector is the force per unit area exerted by the fluid outside so this is in, this is out on the surface, okay, since the fluid is static, okay, this has to be in the direction, I mean, since it is purely normal, it has to be either in the direction of n or opposite to n, but the pressure is normally compressive. So, this is in the direction of minus n, okay, because n is pointing from in to out, whereas the force is from out to in, and the magnitude of the force, compressive force, is pressure. Force per unit area is pressure P. Okay. So, R, this force per unit area, is given by minus P n in a static fluid, because a static fluid cannot support any shear stress. Okay. So, and typically the units for pressure is in SI units, it is 1 Newton per force per area, Newton per meter square. Okay. This is also equal to a Pascal, 1 Pascal, but it turns out that the pressure that is experienced by us in the free atmosphere, it is called atmospheric pressure. So, the atmospheric pressure is approximately 10 to the 5 pascals, it is a large number. So, pressure is normally expressed not just in pascals, but also in kilopascals, megapascals. Kilopascal is 10 to the 3 pascal, 1 megapascal is 10 to the 6 pascal, and so on. So, you should be getting used to this prefixes to these units, which tell you multiples of thousands. Okay. And sometimes pressure is expressed in terms of 1 atmosphere, that is approximately 10 to the 5 pascals. Sometimes it is also expressed, we will show a little later, in terms of columns of mercury in a manometer, it is 760 mmHg. Okay. We will see this a little later once we finish the basics of fluid statics. Okay. Now, let us first worry about what is the nature of pressure. So, if you take any macroscopic volume element in a static fluid, okay, if you take a macroscopic volume element, I have just told you that the force will be purely compressive, force exerted by the surrounding fluid on the surface of this volume element be purely normal to the surface, and it is compressive. Okay. This is for a macroscopic volume in a static fluid. Suppose I consider a point, okay, in a volume and construct a surface. So, construct a surface, this is a point, and I can construct a surface, okay, with some orientation. Whenever I construct an area, there is orientation associated with it, because I can orient this area in many ways. Okay. Now, what is the nature? So, this is really a point, and about this point I construct a tiny area delta A, okay, and I ask the question, what is the pressure measured at this point? Okay. So, I can do this thought experiment. I can orient the surface in one direction at a point. So, I take a point, construct a very tiny small area, and I orient it in a particular way, I measure the pressure, I change the orientation, the fluid is static, okay, and this is really a very, very small area. So, that we are shrinking it eventually to a point, and as I change the orientation, what is going to happen? What is the value of pressure? Okay, is if does the value of pressure. So, we will ask this question, if you do this experiment, does the value of pressure at a point in a static fluid does it depend on n? The orientation of the surface. Essentially, you are considering a point, but about a point you can construct an infinitesimal area. So, as I have told you repeatedly in the continuum approximation, when you say at a point, any property like density at a point, you have to construct a tiny volume about that point. When you consider pressure, you have to construct a tiny area, but you can construct this area with infinitely many orientations about a point. So, does the pressure that one obtains about a point as the area shrinks to 0 in the continuum sense, okay, does it depend on n, the orientation? We will show that it will not. So, the pressure is purely a scalar. That is, at a point pressure is force per unit area, but it has at a given point, if you construct a tiny volume about a point at of arbitrary shape, orientations at the surface, it is always compressive, it is always in the direction in the direction opposite to the unit outward normal. So, pressure does not have a sense of direction at a point, it is the force per normal force per area at any surface of a surface of any orientation that you would construct about a point. Okay. So, how do we show this? We show this in a very simple way. So, you consider, so this is proof that the pressure is a scalar, does not depend on the orientations about a point, many orientations that you can have when you construct an area. Okay. So, let us take a volume that is wedge shaped like this. Okay, and this third direction is so large that we will neglect variations in the third direction. So, consider only the cross section, triangular cross section. Okay. Now, this angle, let it be theta. Okay, sorry. Okay. Now, let us put a coordinate system x, z and y is going into the board, that is not relevant. So, if you consider this x, y into the board and z vertical. Okay. Let us say gravity is acting like this. Okay. So, this is a static fluid. Okay. The fluid is still static. We are interested in fluid statics right now. So, let us not draw y here, it is purely a plane. So, this is x and z. So, let us call this surface. Okay. Let this distance be delta x, let this distance be delta z, let this distance be delta s. Okay. Now, there is also gravity that is acting down. Okay. The pressure at this surface, and these are all infinitesimal lengths. So, the pressure is approximately a constant. The pressure on this bottom surface of this wedge like volume element, let us call it P z, because this is P at this location z equal to 0, and let us call the pressure here at this face P x, and let us call the pressure is acting normally and it is compressive. So, it will act like this on this volume element. Let us call this P n, and by geometry you can verify that this angle is also theta. Okay. So, pressure will act on this inclined plane, inclined surface, that is the stop surface, in a purely normal way. Okay. So, what are the various forces acting? The body force due to gravity is the mass times acceleration due to gravity. Okay. The body force acts only in the minus z direction. Remember, z is going up. So, body force in the minus z direction, in minus negative z direction, is equal to mass is rho times volume. Rho times volume of this wedge is basically half times delta x delta z, okay, times, let us call this width b. Okay. B is very, very large. Okay. So, W times G. Okay. If this were a complete cube, a cuboid, you would say that the volume is delta x delta z times B, but you are cutting it into half by from the across the diagonal. So, it is half delta x delta z W G, that is the body force that is acting in the negative z direction. Okay. Now, we will do a force balance. Okay. So, and along the other surface forces are acting the way we have shown here in the 3 phases. Okay. The surface forces are acting along the 3 faces like this. Okay. So, now let us do a force balance. Force is a vector, so you have to do the balance in component wise. So, x component of the force. So, first of all, what is the force balance? It is a static fluid. So, by Newton's second law, sum of all forces acting on this volume element is 0 because the fluid is static. This is from mechanics. So, sum of all the x forces must be 0 if you are worrying about the x component. So, this is the wedge, along this direction it is, so this is plus x, this is y. Okay. So, along the plus x direction you have the force P x times the area is B, which is in this into the board, times delta z, sorry, this is not y, this is z, that is the way we drew, okay, times delta z. This is the force in the plus x direction in this phase, and then you have this normal force P n. This normal force can be resolved into 2, and this angle is theta, into 2 components. This is theta. Along the vertical it is P n cosine of theta, and along the horizontal it is P n sin theta. If such is the case, okay, then, and it is acting in the minus, so this force is acting in the minus x direction. So, I will put a minus sign times P n sine of theta, okay, times B times delta s is 0. Okay. So, let us put, okay, is 0. This is the x component. Okay. Now, the B factor will cancel right through. Okay. Now, from geometry, delta s sin theta is nothing but delta z. Okay. So, remember that this is theta, this is delta z, this is delta x, this is delta s. Okay. So, sin theta is delta z by delta s, therefore, delta s sin theta is delta z. Okay. So, in the above equation, in this equation, I write the first term as p x delta z minus p n sin theta delta s is nothing but delta z is 0. So, we have shown that by using the x momentum balance, that the magnitude of this force p x must be the same as the magnitude of the force per unit area here. So, p x is p n. Okay. Now, let us do the vertical balance, which is the z component. Okay. So, here the force is the sum of all the forces in the z direction must be 0. Along the z direction, the forces, so remember this is the z direction. Okay. So, the forces are in this plane acting in the positive z direction, it is P z times delta x times b, and then you have in the negative z direction minus P n cos theta, that is the component of the force P n in the vertical direction, but it is negative because it is acting in the minus z direction, and then you have to multiply it by the area of the triangular the wedge area of this surface, because that is where this force is acting, that is delta S times B. Okay. And then in the vertical direction, this is Z, there is gravity acting. So, gravity is, we have already found, this is rho times G times half B delta x delta Z is 0, sum of all forces. Gravity is acting in the negative Z direction, so is this force, which is the component of the force on this triangular surface on this face. Okay. So, we can cancel B right through, okay, and by geometry delta S cos theta is delta x. So, we can cancel this, this and this to give P z minus P n minus rho g delta z by 2 is equal to 0, or P z is P n plus rho g delta z by 2, but in the limit as the volume shrinks to a point, delta z will tend to 0. So, this term will be negligible. So, P z is approximately equal to P n in the limit, and that is also equal to P x. Okay. So, what we end up showing finally is that if you take a point in a static fluid and if you want to measure the pressure, okay, so you will measure the pressure by taking a tiny area, and the area can be oriented in any way. What we have shown with this example is that P x is P n is P z is the same, and it is independent of orientation of the surface. So, we took this wedge, okay, this is the wedge, and we looked at the side face, which is P x, the bottom face, which is P z, the pressure acting is P z, and the inclined surface, the pressure acting is P n, and we find that the pressure must be the same in a static fluid regardless of the orientation of the surface at which it is measured. Okay. Now, we will stop here, and then we will continue in the next lecture, and we will worry about force distribution in a static fluid. Remember that in a static fluid there are pressure forces which are due to the surface forces and body forces. A balance between pressure and body forces gives rise to force distributions or pressure distributions. So, we will continue with this in the next lecture, and we will see you in the next lecture. Thank you.